So suddenly that video stopped recording, which is why there's a second part. Certainly my preference would have been that it not stop recording, or at least that I noticed that it stopped recording 20 minutes before I actually noticed it had stopped recording. So let's see how part two goes. Hey, so we were here graphing this one, y equals -3 secant pi over 2x plus pi over 3 plus 7. Okay, so please give that one a go. Give it a try. This is certainly a reasonable CFA or quiz or test level question, and certainly something worthy of our the graphing portion of our final. Okay. Hey, so welcome back. We've got pi over 2x plus pi over 3 equals 0, and pi over 2x plus pi over 3 equals 2 pi. And what do I graph first? Is it sine? Is it cosine? Secant is the reciprocal of cosine, so I'm thinking about, and it's a negative. I'm thinking about graphing the negative cosine version, and that starts with me finding the endpoints. Pi over 2x equals negative pi over 3. And then, yes, of course, you can divide by pi over 2, but you could also multiply both sides by reciprocal. And so you get x equals -2/3. Over here, this is 6 pi over 3 minus 1 pi over 3 is going to be 5 pi over 3 equals pi over 2x. And again, if I multiply by the reciprocal, I end up with 10 over 3. So x equals 10 over 3. So let's do some graphing. Here's -2/3. Here's 10/3. Halfway in between them, is that 4/3? Sure, we'll add these two numbers together. That'll be 8. And double the denominator. 8 over 6 reduces to 4 over 3. And how about these quarter points halfway in between each? Well, of course we can do the same thing. We'll add these numbers, and that's going to be 2 over, don't forget to double the denominator. 2 over 6 reduces to 1 over 3. And then how about over here? Well, we want halfway between 14, so I'm going with 7. Okie doke. We've got our quarter points. Now we're supposed to graph cosine, negative cosine. So we start low, go to our maximum, and back down again. Remember, we don't want this looking like absolute value. We don't want this looking like a parabola. We want concave up, concave down, concave down, concave up. Show that concavity, especially if you're moving on to calculus. Yeah, that's going to be important for us. I've labeled the sinusoidal axis, and I know that the amplitude is 3. So 7 plus 3 gives me 10 here. 4/3, 10. And here at -2/3, -2/3, comma, this is 7. Our amplitude is 3, so 7 minus 3 brings me to 4. And here we have 10/3, 4 as well. And there's the wonderful negative cosine version. But wait, we're supposed to graph secant. So wherever that cosine crosses the sinusoidal axis, we draw in our vertical asymptotes. And finally, we're just doing our little paraboloids. Little paraboloids. Please, though, either remove this graphing aid or at least make it dotted so that we don't think that you think that, in fact, the graph is both the red and the purple. The graph of this function is only the red stuff here. Huh? Well, except, don't forget to label those points. So I'll circle them, yes, I would need those as well. And I think knowing that this vertical asymptote is at 1/3 and this one is at 7/3 would be fabulous too. Okay, so how about this one? Y equals 1/3 cosecant x over 3 plus 2 pi over 3 plus 5/3. Oh, you're supposed to do this. You're supposed to graph this thing, so please graph that. And come back when you're done and want to check your answer. Hey, welcome back. So we're setting the argument. 0, and x over 3 plus 2 pi over 3 equals 2 pi. Okay, so I subtract 2 pi over 3 from both sides. So x over 3 equals negative 2 pi over 3. And if I multiply both sides by 3, I get that my starting point is negative 2 pi. This is 6 pi over 3 minus 2 pi over 3 is going to be 4 pi over 3 equals x over 3. So if I multiply both sides by 3, I get x equals 4 pi. So this here is negative 2 pi, and this here is positive 4 pi. And halfway in between, is that going to be 1 pi? Well, let's see. Minus 2 plus 4 is 2. 2, double the denominator, I can go 1 down there. So I've got 2 pi divided by 2, which is 1 pi. Yeah, that's nice. Don't forget the quarter points. This is going to be 5 pi over 2. And this is going to be negative pi over 2. We're graphing cosecant, which means we're starting by graphing a sine graph. This is positive, so our sine graph should start on the midline, go up to its high point, and back down before returning to the sinusoidal axis. Okay, wherever that cosecant graph crosses the sinusoidal axis at 5/3, that's where we want to draw a vertical asymptote. Okay. I want you to please label these points. We know this is negative pi over 2, comma, 5/3 plus 1/3 is 6/3 or 2. 5/3 minus 1/3 will be 4/3. 5 pi over 2. And there's our graph of cosecant. Okay? All right, well, please let us know if you have more questions about graphing sine, cosine, tangent, cotangent, secant, cosecant. So I kind of want to move in a slightly different direction now, getting us ready for some subsequent work. And the thought is that we might want to look for all solutions on negative 2 pi to 2 pi for tangent x equals 1. So what do you think we could do to figure out when tangent equals 1? Well, we're going to do a whole bunch of solving equations in our unit about identities and solving, which is coming up. But I kind of want to say, yeah, when does tangent equal 1? But I also have to try and figure out when tangent is equal to 1 on that domain. Now, some people say, well, Mr. Cookley, there are these things called inverse trig functions. Could we use that? And the answer is, well, yeah, but these inverse trig functions, they're only going to find one solution. And I think the reason that this comes up in our unit on graphing, now where it does, is because I can have a graphical understanding of this equation. So, what do I mean by that? Well, we know that tangent has vertical asymptotes at negative pi over 2, pi over 2, 3 pi over 2, and negative 3 pi over 2. Yeah? And tangent shape looks like this. There's 2 pi, and over here, got that one. This is the negative 2 pi. Well, so how many periods do we have here? Remember, the period for tangent is only pi. That's a period. We've got 1, 2, 3, a half, and another half, 4. And each of those periods for tangent, when does tangent intersect the line y equals 1? Well, here's y. That's a little high, actually. Here's y equals 1. and I see 1, 2, 3, 4 points of intersection. If I do inverse tangent, I'm only going to find this one here at pi over 4. So here's what I really like about having a graphical sensibility. I know that I'm looking for 4 solutions. Now, there are some people who say, well, okay, Mr. Kuko, I can do this one because I know that tangent is sine x over cosine x, and that's 1 over 1. So, yeah, when does sine equal 1? Well, careful. The sine equals 1 at pi over 2. And tangent has a vertical asymptote there. So I don't think that's the way we're supposed to do this problem. Some people cross multiply and they get sine x equals cosine x, and then don't know where to go from there. And I can certainly understand that. I've got 2 different trig functions here. I don't know how to make them equal to each other. But maybe we could do a little thought experiment here. Maybe what we should talk about is, when does the upness equal the overness? When does the x value equal the y value on our unit circle? And think about that. We've got our unit circle, and we know over here we have root 2 over 2, comma root 2 over 2. And even over here we have negative root 2 over 2, comma negative root 2 over 2. And when I do the y value divided by the x value, in each of those cases, I'm going to get 1. So, yeah, tangent is going to be equal to 1 at pi over 4, at 5 pi over 4. In fact, if I can find one of those, and I'm going back now to think about my graph, there's negative 3 pi over 2, there's negative pi over 2, there's pi over 2, and 3 pi over 2. Okay? And we have these inflection points. But our assignment, the question we've been asked to wrestle with, is tricky because we know that not only will we find this solution, pi over 4, and we just found this solution, 5 pi over 4, but since these are pi apart from each other, we could actually just subtract pi from this to get negative 3 pi over 4, and subtract pi from this to get negative 7 pi over 4. So I think, actually, I don't have to do much of an algebraic approach if I can determine that what I'm looking for is the place where sine and cosine have this same value. So that when I do tangent, I'm thinking about tangent as sine over cosine. And then, I didn't need to pick up a calculator for that. I just had to think. In fact, I could really just make it be so that between 0 and pi over 2, there's a solution. So I think about my unit circle, and I think about first quadrant, and I think, well, when can tangent be equal to 1 in first quadrant? Oh, 1 comes when these x's and y's have the same value. So that must be pi over 4. And then I simply need to use the period to figure out these other solutions. But I'll say this, some students I've talked to say, okay, yeah, no problem, I found pi over 4, and I added pi and got 5 pi over 4, but then I added pi and got, wait a second, 9 pi over 4? And then there was this other one, 13 pi over 4? Yeah, no, those wouldn't be any good. How come? Well, remember, we were asked in this question to find all the solutions between negative 2 pi and 2 pi. And so when I did this graphically, I thought about, okay, negative 2 pi to 2 pi. I'm building that vision of this situation. I'm building that graphical understanding that this curve is going to intersect this curve. But what I see on that domain is not just one solution, but 4 solutions. And conveniently, I know the period of tangent is pi. And so I'm going to add pi one time to get that one, but I have to subtract pi 2 times to get these others. By which you might want to say, well, Mr. Yuka, how am I supposed to know when I'm supposed to add pi or subtract pi, and how many times? And the answer is, I look at the graph. I look at the graph to tell me, oh, there's these 4 points of intersection from here to here. 2 of them are between negative pi over 2 and 0, and 2 of them are between 0 and pi and 2 pi. So, yeah, I think this is a good thing for us to be thinking about. And I really do know that having that sort of graphical understanding of algebraic things, yeah, that's worth us thinking about. Now, I will say secant theta equals 2. And again, let's think about negative 2 pi to 2 pi. Okay? You could do this a couple of different ways. You could graph secant and say secant whenever u equal to 2. So cosine is 2 pi. Why am I drawing cosine? Well, I'm drawing cosine for one of 2 reasons. And that reason is 2, 2, one reason could be because I'm drawing secant, and that means I draw cosine first. Or I could just re-envision this problem. Instead of secant equals 2, I could flip both sides because this is 1 over cosine. If I flip both sides, I'm going to have cosine theta over 1 equals 1/2. And when does cosine equal 1/2? Well, here's cosine. Here's equal to 1/2. Again, I have 4 solutions. And if I think about it, where between 0 and pi over 2 is cosine, the x value, 1/2? Well, that happens at pi over 3. Now, how far is it from here to here? Yeah, no, that's not pi apart. Students often think that's pi apart, but that's not pi apart. In fact, we want this place where the cosine graph is decreasing. So that's over here. And the distance between these, well, that distance from this one to this one, that distance is 2 pi. So if I've got this solution, and I subtract 2 pi, or 6 pi over 3, I get negative 5 pi over 3. And then here's another unit circle question. When is it that cosine is equal to positive 1/2 on 0 to 2 pi? That happened here at pi over 3. It also happens in the 4th quadrant at 5 pi over 3. And then we ask the question, okay, well, how far is it from this one to this one that looks just like it? They're both on the uphill. And the answer is 2 pi. So if I take that 5 pi over 3 and subtract 2 pi from it, that's going to be 5 pi over 3 minus 6 pi over 3, or negative pi over 3. And so in this situation, I get the answers negative 5 pi over 3, negative pi over 3, and then positive pi over 3, and positive 5 pi over 3. Those are the answers in this situation. Okay? No algebra was done. I didn't even need to worry about the secant. Well, in fact, I did worry a little because that gave me that cosine was equal to 1/2. So that's what we're talking about here. Now, of course, if calculator is permitted, you are more than welcome to graph and do second calculate intersect. That could be a fine way to do this problem as well. But if I'm really comfortable with my trig graphing, with my knowledge of period for sine, cosine, secant, cosecant, and the last problem, tangent or cotangent, I should be able to find these with very little suffering. But they are different, and so you might want to practice some more of those. Okay, there's not a lot more I want to talk about here, but I do want to get 2 last things done. This is something which I think is always very interesting. Because I always think that everyone knows how to do this, and in fact, most people don't know how to do this. the directions here are specific and explicit, and so I would encourage you to write these directions in your notes. Write theta as a function of x. Okay? Theta as a function of x. Now, when we were doing the functions unit last semester, we said that this grammar meant that theta should equal some x stuff. Yeah? So like theta equals 2x plus 1. That's theta as a function of x, right? And input is an x as a function, that's the input, and this is the output. Okay, that's what this grammar, this English grammar is telling me, that this is what comes out when I plug in an x. So I'm plugging in x values here. Okay? But now look at the question we've been asked. We've been asked to, for this picture, write theta as a function of x. Now, please note these directions, because this is a question that often gets left blank on tests and quizzes, because students don't know what that means. Well, we know that when we look at this picture, I've got the opposite side and adjacent side. Well, which trig function would that be? Opposite and adjacent? Oh, well, that's tangent. So I could write tangent theta equals 7 over x. But notice the question was, notice the question was, write theta as a function of x. The question wasn't write tangent theta as a function of x, so I'm not done yet. And what is it that I still need to do? I need to get theta alone. Now, if this were tangent tan times theta, then I would divide both sides by the letters tan. But that's not the case. No, this is tangent of theta. This is a function, and I need the inverse to undo this thing. And so I'm going to take the inverse tangent of both sides. Inverse tangent is the thing that cancels tangent, leaving me theta. And now on the other side of the equation, there it is. The input is x, the output is theta. Here, theta as a function of x. X, I get out of theta. Brilliant, that's it. That's all we need to do. But if I don't understand these directions, there's no way I'm going to say, well, I guess that's going to be the inverse tangent of both sides. So really, you definitely probably might want to write this one down. Yeah, it's funny because I notice that students are really, really, really good at all this graphing too, and that most of the mistakes on the graphing just come from little things like adding or subtracting, or trying to find those quarter points. But also, what should I set what's in the parentheses equal to? So let's go through that again. Here's our trig function. And here's what we set equal to. Okay, so with sine, cosine, and because we know the reciprocal secant and cosecant have the same period because they're just reciprocals, cosecant and secant. We set those equal to 0 and 2 pi, and if someone asks you for a second period, use 4 pi. Okay. Now what about tangent? That's right, tangent is not this. Tangent is negative pi over 2 to pi over 2. And then finally cotangent. Well, these vertical asymptotes on tangent become zeros on cotangent. So where are the zeros on tangent? Well, the zeros on tangent are at 0 and pi. So that if I flip, these become places where tangent would be, where cotangent is undefined, and I have vertical asymptotes. Okay, so these are finally vertical asymptotes. All right. Ooh, and I guess I kind of want to put that column down as well. Let's put it over here, period. So the period for these four is 2 pi. The period for these two, pi. All right. Well, I hope this was helpful. Sorry that the video stopped recording and I had to continue. Is it happening? No. Phew. All right. Take care, everyone. I'll see you in the next video.